So those are two ways that waves can move through material. It's a transferring of energy through material or through an area. But I do want to make just a quick mention. There are two kinds of substances, types of waves that can pass, which we have been mentioning as examples up here, is that mechanical waves actually propagate through material. So the ocean has a mechanical wave passing through it. It's actually a potential wave. You're lifting the water up, which has more potential as it's moving through, and then it returns the water back to normal until the next wave comes back through. It's a potential wave. Sound is a pressure wave, also potential, because higher pressure air has more potential to do work. But there can be other kinds of waves, and they can pass through space, but not through material. And they'll be passing through a field. A field is just a general space. It doesn't have anything in it, but it does have values to it. So if you think about the voltage that's in your plug at the home, at 120 volts, for instance, you could make, for instance, the electric field vibrate or go up and then come down, go up and then come down. So you could change, you could let an energy pass through in the electric field. Other places could be like the magnetic field. Magnetic field is if you took a magnet and you waved it back and forth, that'll radiate out, or you can just hold it, it'll create a field around it. But if we change it by just moving that magnet or rotating it fast, for instance, you'll create a field, or sorry, a wave that is propagating magnetism, or magnetic field strength. It'll be North Pole, South Pole, North Pole, South Pole. And also, we talked about all the gravitational waves. Gravity can be what is driving or what is being changed, the gravitational potential in an ocean wave. Gravity can also pass through space. If you take a large object and you move it back and forth, the only times you really see these are in rare cases when there is, for instance, two stars that are really close. They're binary star systems and they rotate around each other. They can rotate very, very fast. As a matter of fact, that'd be the rare occasion where you can see them, and that's where they have proven that there are gravitational waves that are being radiated out. So a mechanical wave actually goes through matter. A field wave is going through just fields like magnetic fields, electric fields, or gravitational fields. What we call light is actually a combination of both electric and magnetic, and so that's why they call them electromagnetic fields. So those are the two kinds of ways we think about waves. One is the way they propagate material when energy is passing through. Perpendicular to the wave motion is a transverse. If it moves with the wave, in other words, the particles move back and forth as the wave moves through, that's going to be called longitudinal. And if it travels through matter, it's going to be a mechanical wave versus a field wave. Now, waves also have properties. As waves come by, here are some examples of properties that they could have. The distance, for instance, from one top of a wave or bottom of a wave to the next, that we're going to call these bottoms troughs. Tops, they're going to be named crests, or the tops of the waves. But that distance between there is, for instance, wavelength. There's also the amplitude. How much power is being transferred is a measure of the amplitude. That power is going to be the distance from sea level, or the non-disturbed state, up to the highest peak. The highest peak to the bottom is not the amplitude, although a lot of people will realize that's something of, how big a wave may seem. You say, oh, that's a 30-foot wave. When surfers are talking about those, they're actually measuring the top of the wave to the bottom of the following one, which will usually double the height of the amplitude, or it's half the distance from the peak to the trough. The last one is how fast the wave, any top of a wave, is moving. That is called the velocity. Now, velocity, frequency, well, I missed one. Frequency is going to be how many waves pass you by in a second or a minute or an hour. Most of the time, we give it the symbol hertz for how many waves pass you by in a second. And that's this person counting the waves coming by. There is a relationship of how fast a wave is traveling. If you know how long every wave is and how many waves pass you by, just think about that. 10 waves pass you by every second, 10 waves, and each wave is 2 meters long, so 10 groups of 2 meters passes you by. How fast is that traveling? Well, 10 groups of 2 meters is 20 meters, passes you by in a second. And so we saw from velocity, 10 times 2 is 20 meters per second is the speed of that particular wave. Now, two phenomena that we're very interested in is sound and how fast that travels. That's going to travel at 344 meters per second. If you remember our little comparison that we had from the motion chapter, it's double and a little bit more, so it's well over 700 miles an hour is the speed of sound. 700 miles an hour, of course, is what you need to accomplish in a plane in order to get to be Mach 1. Mach 1 is the speed of sound. Mach 2 is twice the speed of sound. Okay. Velocity of light is even greater. As you can see in the notes here, that's 300 million meters per second. That's mind-numbing. So most of the time we say we see things instantaneously when we're talking about from us to another place on the Earth because it travels so fast. But you could talk about, places that are much more than 300 million meters. And that's just 300,000 kilometers. Of course, if we move the decimal over, it's just kilometers, there's 3 places left. 300,000 kilometers is only a fraction of the distance to, for instance, even the moon. Well, it's a healthy part of the distance to the moon, but it's a fraction to the sun. As a matter of fact, light from the sun takes 9 minutes to get to us. So we see the sun now like it was 9 minutes ago. If we look at a further star, that's going to be the closest star is about 4 years away, and that might be called a light year, how far travels light in a year. The sun is 9 light minutes from us. It takes 9 minutes for light to travel that. So even though this is super fast for light, it does take some time to travel. So frequency is going to be related to how fast something travels and how long every one of those waves are. You're going to get the chance to do a couple of problems today in the front part of this worksheet to change between velocity, wavelength, and frequency. So give that a try right now.